Hello. Today I'd like to talk about classic motion planning techniques. These are the today class objectives. I'd like to talk about classic motion planning techniques, including roadmap, cell decomposition, also these potential fields. Details about these techniques actually covered in the chapter 3 of my draft, whose links are available here. Before we move on, last time we talked about the configuration space, representing the freedom of the robot, and also we talked about the discretization of the C space, especially the free space. And then, as an example, we talked about the visibility graph. And then we can use the different search techniques to find the path from the start and goal on the graph. As an example, we can use the best first search. Also, we talked about A-star techniques. Also, I went over some of your questions, and one of you actually mentioned that I'm still in the Italy, which is 7 hours behind. So basically, I mentioned that when I give some quiz on Thursday, you need to do you need to finish that taking the quiz within Thursday, right? So that should be, but you can do that with, in your time zone. So basically, if you're in the another country, let me know. So he or she is in the Italy, so I can know his time zone. Also, some of you asked, can you send me some background publication in this field? There could be the many paper. I mentioned that you can find the paper on the Octree and IROS, but the more important information is that go over my draft. So here actually, I talked about through this YouTube, I talked about main idea. But if you're unclear about some of the components, I strongly recommend you to go over my draft, which I'm trying to improving right now. So basically today I will talk about the roadmap, the cell decomposition, potential fields. First of all, I would like to talk about the roadmap, which is its main idea is that it tries to represent the connectivity of the free space in the C space as a network of the 1D curves. So this is actually one of the example of the roadmap. So last time we talked about the visibility graph, right? That's also the example, one of the example of the roadmap. So basically, in each edge in the visibility graph is kind of the possible road that we can take, right? And another example is this Brunner diagram, which is introduced the computational geometry research a long time ago. So this is example of this Brunner diagram. This is actually obstacle, and then given that this kind of workspace, we actually we can run this diagram Brunner diagram algorithm. But basically, the Brunner diagram is nothing but it maintains the equal distance from the distance from the boundary of obstacle. For example, here actually we have the obstacle here, another obstacle there, and then we actually compute this middle point here. That actually maintaining the same equal distance from that boundary to there, also another distance from this boundary to there. So basically, the main feature of the Brunner diagram is that this is a Brunner diagram. Then based on the Brunner diagram, we can generate paths that maximize clearance. In other words, we can maintain maintain the best clearance. In other words, the best empty space from here to there, or from here to there. So that's one of the main benefits of the Brunner diagram. So we can lowering down the probability of hitting the obstacle. And there could be the different algorithm actually, but there's one of the efficient technique that has analog and time complexity by sweeping through this kind of point. Actually, this is one of the illustrations. But also this time complexity is mainly for the 2D. When you have the high dimensional one, it gets much more computation. Also, there's a technique that we can use the GPU computation to approximately computing this Brunner diagram. So another technique is a silhouette technique. I'd like to briefly touch on the silhouette. This is one of the first complete general motion planning technique. Later on, I'll define the meaning of this complete. This one of first complete general technique that applies to the space of any dimensions of the DC space, and also it has a singly exponential in terms of the number of dimensions actually. So back then there is a complete motion plane technique, but its time complexity actually has this double exponential here in the as a function of the number of the dimension here, the n. So as you can see, as we get the higher dimensions, in other words, as we get the more complicated robot, it's very it requires double exponential the slowing down of the motion plane algorithm. But this similar technique enabled this single exponential time complexity as a function of as a number of the dimension actually. And then a lot of the recent technique used this probabilistic approach. So this is exact complete method. But actually, in most of case, actually we don't have time budget to actually run this kind of complete method. So to make the more practical technique, we can actually allow some sort of error. So that's why there is actually approximate technique known as the probabilistic roadmaps, which I will talk about later on. And also this is actually one of our prior technique that used this Voronoi diagram to guide our sampling to guide the motion planner to find the optimal path better. So let me show you the video here. So given this actually obstacle, and then this is also the wall, and then the black curves actually representing the computed Voronoi diagram, and then we wanted to compute the path from here to there, and then here we assume that this car model like this kinematics car model that I mentioned before. It's very slow. See. Basically, first of all, we need to compute the Voronoi diagram, and then we actually generate samples. But we generate samples near the Voronoi diagram, since if we follow the Voronoi diagram, there is higher probability that we can compute the optimal path. Actually, in the 2D case, there is a theorem that optimal path actually can map to the one of this Voronoi diagram. Here, this is the start and goal. As this actually also will require this it use the RRT star, which is based on the probabilistic optimal planner, which I will talk about later on. But anyway, you can use this classical technique concept of Voronoi diagram to improve this recent techniques. Oh, sorry. Now I'd like to move on to this classical technique, this cell decomposition. Let me show you this example. The cell decomposition technique, as you can see from its name, it decomposes the free space into simple cells. So here actually I will show you this trapezoid cell, simple cells, and represent the connectivity of the free space by the adjacency graph of these cells. There are two types of the techniques. One is the exact, also the exact or the approximate techniques. Exact cell decomposition is that each free space F is represented by a collection of the non-overlapping cells whose union is exactly same to the free space. One of the examples is actually trapezoidal decompositions. So it might be better for you to look at this example here. This is obstacle, start and goal. We want to compute the path from here to there. And to do that, we actually here we first of all we identify some of the important event. And here actually along the bodies, a lot of things actually changing. So we look at these bodices, and along the bodices, we can actually decompose this free space as a set of these trapezoid. Actually, you can see this is one of the trapezoid. This triangle actually the one of the reduced reduced after this trapezoid. And if we actually compute the trapezoid along that way, then for each trapezoid we generate node here, And then we look at what are the adjacent, actually the neighboring the cells, and then between those cells we compute the we compute the edges here, and then also we generate another node, and then we compute the edges here. Based on that, we can compute the actually adjacency graph, which is the another discretization example of the free space. And then out of this graph, we can actually run the search algorithm to find the path. So there are actually many different ways of this trapezoidal decomposition. One of the techniques is a critical base approach, utilizing these vertices. And then here actually they actually I don't want to talk about all the low level details here, since this kind of technique actually mainly coming from the computational geometry, which is actually very different from our discussion that we will do throughout this course. So that's why I'd like briefly touch on this topic, and then we sort these vertices. So that's why actually I mentioned the planar sweep approach. Since it requires some sort of sorting, it has a time complexity of the n log n, which is very common, the time complexity when it deals with the sorting. But anyway, it actually requires n log n in a very simple setting 2D case. Obviously, when you're considering more higher dimension, it actually as you can see, as I mentioned in the silhouette technique, a lot of the exact technique turn out to be has this exponential time complexity. So one of the main methods is that you should avoid using these exact techniques. Anyway, so I mentioned this exact approach. Now I'd like to talk about approximate technique. One of the key distinctions is that this also free space F represented by a collection of non-overlapping cells, but the whose union is contained, not exactly the free space, but contained. And we typically use this Octree and Quadtree like approach. Let me show this example here. This was obstacle. Then we decompose the free space with the Quadtree. Quadtree is nothing but we actually, given this cell, we divide the cell into the 4x4, and then we keep doing that until each node. That's why I mentioned that it's the hierarchical space decompositions. We keep hierarchical refining until the sum of nodes actually fully contain the free space, also the optical space. And then we decompose the free space F into the cells, and then we keep doing this process. We search for a sequence of mix of free cells. Basically this free cell, and if we find the free cell, it is guaranteed that we can pass through the cell without having any collision, right? Mixed cell means that within that cell, there are some portion of the cell is that has an obstacle, and the rest of cell didn't contain anything, right? So that's why we said the mix. So it's unclear whether we can find the path or not within this mixed cell. But anyway, we find the sequence of mix of free cells that connect the initial and goal. And then since the mixture is unclear yet, so we decompose those cells of this mixed cell until we can find the sequence of free cells. So once we find the sequence of free cells, it means that between the start and goal, it means that we find the collision-free path, right? So that's one example of the approximate cell decomposition. Based on that, we can compute the path. And in the 3D, also we can use the Octree, right? Given a cell, given a space, we decompose into eight subcells, and then we keep doing that. Same concept with the 2D. Okay, so far I talked about the roadmap and cell decompositions, right? And then the last one is actually potential field. Its main idea is that it defines a function, some sort of value function over the free space that has a global minimum. It's a kind of potential, right? It actually has you can treat the potential as some sort of energy. Has a global minimum at the goal configuration, and basically we wanted to compute the paths that lead to this global minimum in terms of potential. This is actually one of the examples here. This was the workspace start and goal, this obstacle, and our goal is that somehow we actually generate potential over this space. Actually, this visualize one of the example of the potential field. Here at this as start and goal. Here since this goal should be here, we should have the lowest potential, right? So we generate that we generate potential field at that way. And then we also we had actually higher value here. Probably starting here, and then to find the path, we look at the neighboring cell, and then we follow the cell that has a lower energy, lower potential. We keep doing that so that actually we can reach the goal. So basically, at the goal, we should have the lowest potential. So this technique initially proposed for a long time ago for real-time collision avoidance. Basically we want to compute the collision-free path, right? To do that, we need to avoid any collision, right? And then to do that, we use scalar function, potential field over the free space. And then once the robot located here, we can compute the force, right? Force that can move the robot proportional to this negated gradient of the potential field. So basically, at that point, we got this some sort of the gradient, right? And then we take the gradient, they can generate the force that push the robot. At that case, the gradient locating, they're generated along that direction, right? If you negate it, then we can push the robot at the downwards, right, to reach the goal. That's why actually we compute the force proportional to the negated gradient of the potential field. So let's look at how we can compute this potential field. There are two different fields. One is the attractive, the other one is the repulsive field. So here, our goal is that we wanted to reach the goal while avoiding this obstacle, right? So attractive field is that we need to guide the robot from starting to the goal, right? So we need to attract the robot to the goal, right? So initially we had a high value here and low value at this goal, and then we generate somehow the smooth function like this, and then we have to repulse our robot away from the obstacle, right? So we typically generate very high value, high potential along on the boundary or nearby the obstacle. So we get this kind of the repulsive field, and if we summing up, then we can generate this kind of potential field. Basically, this potential field concept is very simple. Also, once the robot located within this one, we can actually very easily compute the force or the control that can guide the robot into the goal. But there are a lot of issues actually. First of all, what might be the ideal potential field? Then we define what's the ideal one. Basically, the ideal potential field should satisfy this kind of property. First of all, it has the global minimum at the goal. Also has the no local minima. I will talk about this concept of local minima. And then also it should grow to the infinity near the obstacle, so that we should not get close to the obstacle, right? And then also everything should be smooth. Otherwise, we're giving the force here abruptly at the robot, and there might be there could be a lot of issues in terms of controlling the robot, right? The question is that how can you compute this kind of one actually? But it turns out it's a little bit difficult problem. This is actually the local minima, the example here, the start and goal. Some other obstacle located at that way, so that's why we got this kind of the mountain like this kind of potential field. So if we take the negative gradient, then at the start, then we push the robot from here to there, right? But once we reach there, we cannot overcome this kind of the high potential field, right? To reach the goal, we should find the path that circumvents this obstacle, the high potential, and getting out of this one, and in other words, getting out of this local minima and define the path, right? But the question is that how can we generate the kind of potential field to avoid this kind of local minima? It turns out to be a very difficult problem. One simple choice is that we can escape the kind of local minima by taking the random walks. Yeah, but again, the question is that somehow we can generate random walks, and then they may put the chance that we can getting out of the local minimum. But the issue is that how many times random walks you should take, and how big random walks you should take, right? But generally, it's a very difficult problem. I'd like to give this overview of this potential field algorithm at one time. Given the regular grid on the Conf space, you compute the potential field first, and then actually based on this potential field, you can compute build the potential field on the grid, and then based on that potential field, also you can run some other the best first search algorithm or some other other techniques by treating this grid as some sort of graph, right? Given a cell, we look at the neighboring cell, and then we can compute actually we can compute these edges, right? That way we can build a very we can build a graph, and then by using this kind of the graph search function, you can also find you can consider the total paths and other ones. So before I talked about the concept, I mentioned that the silhouette technique is one of the first actually complete motion planner. Then we define what complete is. A complete motion planner, it indicates that complete motion planner always returns a solution when the solution exists, right? If there's solution, the complete motion planner should return the planner, right? I mean, there's a lot of cases that there are solutions, but sometimes we may not able to find it, right? That's not the complete one. The complete one is that we always return the solution when this exists. Otherwise, if there's no solution, the complete motion planner say that we cannot find the path. That's the motion planner. Then so far we talked about many different the techniques. And now let's talk about whether they are actually complete or not. For the case of the visibility algorithm, it will be the complete one. Yes, it will be the complete motion planner. If there's actually the path, the complete motion planner can give us the path. So basically, we'll look at all possible actually the cases. The cases out of based on this visibility concept for building the visibility graph. So that's why actually we can design a complete motion planner, but it comes with a high computation cost, right? Exact cell decomposition also it can be the complete motion planner, but for the case of potential field, if we're just using a very simple approach of this potential field, even though there's solution that we can actually find the path from here to there, we might stuck into the local minima, and then we might not able to find the path, right? That's why the potential field is not a complete motion planner. But anyway, basically the completeness, the properties is one of the very useful techniques. But also there are many other properties that we need to have. Another one is the optimality. We can we can find the path, but if the path is too long, it's not useful, right? So we should be able to find the path. Also, that path should be the good one, right? So far I talked about the basic motion planning concept, also the different the classical motion planning one. But usually actually it's better for you to try out some of the actual tool and then see how we can compute the path, right? But actually there are very well-known open motion planning library, OMPL. It's open source, you can download it. I heard that it used to be very difficult to compile, but now it becomes relatively easier. And then if you actually the link and then if you download it, you can try it out different scene and robot, and then basically go over the create a scene. You don't need to create by yourself. I know that you can choose the scene, and then you can actually use that existing scene and choose your existing robot, and then by clicking some of button or by using some of the API, you can actually I know that you can very easily find the collision-free path and visualize the result like this. So I'd like to recommend you need this actually PA1. So try now the library tool, and then doing the set up the basic scene, and then see how you can compute the path. You don't need to implement any complicated algorithm, but by doing this homework, you can get a much better idea about how you can compute the path. So there will be the more detailed spec at the homepage, which will be given by TA. The deadline is the September 21st, and then submit the image that shows the scene with the robot with the computer path. Submit that image to the KLMS, and then TA will go over it. So basically there are actually many conference deadline. So basically the ICRA the deadlines I heard that it's on the October 15th. We don't have much time, but I recommend you. I wish that some of you conduct a very interesting research as a final project in this course. Maybe you can submit it. You can also you can keep extending that technique, and I hope that you can submit it at the next year. And also there are other conferences like RSS, also the IROS. So the last year actually ICRA 2020 was scheduled to held at the Paris, but due to the COVID-19 we don't have this conference. It's it was really pity that we cannot visit the Paris. I hope that COVID-19 issue will be resolved soon so that we can actually interact again. But anyways, today I talked about the classical motion planning techniques, including roadmap, cell decomposition, potential field. If you want to know more about details about this technique, I recommend you to go over this chapter 3 of my book. Same homework, browse the two video and the papers and submit each summary through the online link here before the every Tuesday class. This is one example of summary. You can write down English and Korean and go over the next lecture slide before watching the YouTube. So that way you can be more ready to take this course. And then if you have a question, come up with the question, write down the questions and at the link. So you just need to write down the two questions 2 times before the midterm exam. It's not a lot of homework, but I'd like to encourage you to come up with the questions. And that's it. So the next time I'll talk about the details about the DC space. That's it. Thank you. Bye.